reaction, that's very simple because you can see there are two things which are getting added to both the carbon atom. Okay, and there is a double bond. Okay, double bond is broken. Okay, and you have H and X. X is C and Br or I. Okay, that is added to one of the carbon atom and H is added to another carbon atom, right? So tell me what kind of addition it is. Is it electrophilic addition? Is it a nucleophilic addition? Is it a free radical addition? Yes, Amara, tell me.
So can you repeat?
Yeah, what kind of addition it is? Is it this is addition reaction? Is it electrophilic? Is it nucleophilic? Or is it a free radical addition? If you don't know, not a problem. We will discuss it in detail. And how to judge what kind of addition is it? That also we will see. Okay. So what kind of addition is it? Addition of HCl. Any idea?
No, sir.
Okay, no problem. This addition is actually electrophilic addition reaction. Okay. So what are electrophiles? This is an electrophilic addition reaction. So let me ask you one thing. What is electrophile? What is an electrophile? So electrophile is a species which is uh, which want to accept electron. Okay. Yeah, Pavitra, can you hear my voice?
Yes, sir.
Okay. So I was discussing the preparation of alkyl halide from alkenes. Okay, and this is addition reaction. Okay, that's what I told Samira. And addition reaction means you know what is addition, and can you see this is an addition reaction? Why can you say that it is an addition reaction? Yeah, Pavitra. Because
Hydrogen is being added.
yeah, hydrogen and chlorine are getting added to both the carbon atom, which were earlier connected with double bond, right? So this is an addition reaction. Okay. Now the next thing is what. So I was discussing the same with Samira that what kind of addition it is. So is it electrophilic? Is it nucleophilic? Is it free radical? There are three types of addition, and in the whole chemistry, organic chemistry, we will see different kind of addition reaction. So as I just told that it is an electrophilic addition reaction. So first of all, I would like to ask what is an electrophile? Okay. So the name itself is telling what is an electrophile, what an electrophile is. The name suggests electrophile. Okay. So it is electrophile means electron loving species. The species which wants to accept electron. Okay. The species which is itself electron deficient and it want to gain electron, that is known as electrophile. So can you give me some example of electrophile, Samira and Pavitra? What are the examples of electrophiles? Generally, what we do, we write electrophile as E plus. but that doesn't mean that all electrophiles are plus. There are neutral electrophiles also. Okay, so can you give me some examples of electrophiles, the species which are formed during the reaction which want to accept electrons? Like H plus. Okay, H plus doesn't have complete electron, complete shell. There is in fact no electron at all. It is just a proton, so it is an electrophile. We have CS3 plus as an electrophile, right? Okay, we have X plus as an electrophile. Okay, and in different condition, different electrophiles are generated. Okay. So as I told you, this addition is electrophilic addition reaction. Means it is the electrophile is responsible for carrying out this addition reaction. Okay, because you take HCl. Okay, and how this reaction happens. In order to understand that, we need to know how HCl behaves. So Samara and Pavitra, can you tell me how HCl behaves? It is an acid. Yeah. Tell me quickly. HCl breaks into H plus and Cl minus, right? Yeah. So it dissociates into H plus and Cl minus. Now, Pavitra, the next thing is, which is it, the H plus or Samara, is it the Cl minus? Who is going to go and attack on the alkene? Yeah, tell me this. Who will go and start the reaction? Is it the Cl minus or is it the H plus? Yeah. Yes, Samara?
H plus,
H plus. Why H plus?
because it is an electrophile.
Yeah, it is an electrophile, but why electrophile? Why can't Cl minus go and attack on alkene? Yeah, what you said is correct. Actually, if you look at alkene, there are two bonds, right, Pavitra? There are two bonds and there is one sigma bond. The sigma bond, the first bond which is formed between the two atoms is sigma bond, and its electron density is along the line joining the atoms. Okay, and the pi bond is formed by overlapping of orbitals which are above and below. That is formed by side overlapping. Okay, so the electron density of the pi bond is not in the molecule plane, but it is above and below. So if we have an ethene, which I have shown you, okay, we can think that this ethene actually is what? It is the pi electron density. It is electron density which is there of the double bond above and below the molecule. Okay, when this pi electron density is there, so this is negatively charged electron cloud, and whom you can expect to come and join to this electron cloud? Is it the H plus which can come and join this electron cloud, or Cl minus? Yeah, tell me. It is the H plus which can come and join this pi electron cloud. It cannot be Cl minus. The reason is, yeah, what could be the reason? Yes, Amira, Pavitra. The reason is the Cl minus is electron rich, okay, and it has already having a lot of electrons. That's why it is minus. And if it comes near the pi electron cloud, it will be repelled away. Okay, so Cl minus you can't expect to come and join on the double bond. It will be repelled away. Cl minus is nucleophile. Okay, it is a nucleophilic species, means nucleus loving species. it has electrons, already having a lot of electrons, so it needs some atom, some positively charged atom, some electron deficient atom where it can go and give its electron pair. So Cl minus is a nucleophile, and nucleophile will be repelled away by the pi electron density. Only the H plus can go and attack on the double bond, right? Because H plus H plus wants electron. It is electron deficient, and your alkene is having a lot of electrons in the form of pi electron cloud. Okay, so now what happens is the CS2, and that's why it is known as electrophilic addition reaction, because electrophile attacks and then the reaction or the addition starts. That starts with the attack of electrophile. So H plus will come here. It will pull the pi electron density. The pi electron density, which is there like this, and the H plus is coming like this. Okay, so it will get shifted like this. Okay, so we will have this kind of structure: CS2, CH, 2H. Okay, you can write it completely. Okay, this is the plus which is forming, and this is the carbocation intermediate which is forming with the attack of H plus. H plus will go and take away, pull both the pi electrons outside, and will use those pi electron to join itself to the carbon atom. What will happen to the other carbon atom? That will have a plus charge. Okay, now the plus charge. Now this has become the electrophile. This ethene molecule now it has become electron deficient. Okay, because it is having plus charge, and there is a Cl minus. Okay, now which came with H plus. Okay, in the HCl. So now this Cl minus can go and attack, join itself. So now Cl minus is nucleophile, this is electrophile. Okay, it will go and join itself to the C plus. So that's how this addition occurs. So this step is slow step. Remember this. A lot of questions come every here. And slow step is the attack of electrophile, attack of H plus, and which lead to the formation of carbocation intermediate. So more stable a carbocation is, higher is going to be the stability of, or the faster is going to be the reaction. Okay, so more stable a carbocation is, more quickly the reaction is going to happen. Clear? Rate is, because this step is RDS. Okay, so this is fast step, you can write. So the reaction, this is the overall reaction. Okay, but this is not telling you what is happening internally, step by step procedure, Pavitra. Samaira, to know what is happening internally, step by step procedure, we have written a mechanism. Okay, so first we understood what the structure of pi bond look like. It is electron rich, H plus comes, H plus is the electrophile, and electrophile can come and join to the double bond. But that step is slow step. Okay, it is the rate determining step, RDS. Clear? You can write it in your notes. It is RDS, rate determining step, because slow step, the whole speed of whole reaction depends upon the slowest step. Okay, right? Because the slowest step is, if it is slowed down further, the reaction will slow down. But if you do something, or if due to some reason the slow steps can occur more quickly, then the whole reaction is going to occur more quickly. The fast step is already very fast. Okay, that is not playing a decisive role. It is just like, suppose a group of people is going to picnic. Okay, a group of people is going to picnic, and the speed of the whole group will depend upon the speed of the slowest person. Okay, so in a same way, because until unless the slowest person moves ahead, the whole group can't go and leave him back. Okay, the fastest person is not going to affect the speed of the whole group. Okay, similarly in chemical reactions, the rate of the overall reaction depends upon the rate of slowest step. Okay, and the slowest step is the attack in this reaction. In addition reaction, the slowest step is the attack of electrophile. or which in this case is H plus on alkene. Yeah, is it clear? Any
Yes, sir.
doubt in this? Darshan, just I was trying to explain how the addition of HX, HCl, HBr, HI takes place on alkene. Okay, so I hope this is clear to all of you, right?
Yes, sir.
Okay. Now the next thing is this one. This is addition of HBr. The next reaction is, so HBr goes and attack. First the H plus goes and attack. Okay, the double bond, the pi electron density of the double bond is taken away by the H plus. The carbon plus forms on the atom adjacent to the carbon atom where H plus has joined itself. Then wherever the plus is, there you have Br minus joining itself. Okay, so this is addition reaction. Okay. Similarly, Hi you can add, so H plus will come, but you need to think of this mechanism only if Pavitra, Samaira, and Darshan. If someone asks you, or it is a mechanism related question, then only you need to think of it. The H plus will come and it will join itself by taking the pi electron density. Okay, you will have this kind of thing. This is carbocation intermediate. Okay, this is the slow step. It is attack of H plus, and then the I minus comes and attack on the carbocation. Is it clear?
Yes, sir.
Yes, sir.
Okay. So now the next thing is this addition is the next thing is you need to write is Markovnikov addition or Markovnikov addition. Addition of HX. HX I am writing in a general way. It can be HCl, HBr, HI. Okay, HF doesn't is not used because it is slow, very slow. So addition of HX on HCl on alkene, sorry, is governed by Markovnikov rule. So what is this Markovnikov rule? Yeah, tell me, who is going to tell me Markovnikov rule? Yeah, Hanifa, what is Markovnikov rule? Darshan, any idea? Pavitra, Samaira?
When an unsymmetrical alkene is added, no. When an unsymmetrical reagent is added to an unsymmetrical alkene, the negative part of the atom gets attached to the carbon containing less number of hydrogen.
Yeah, exactly. So addition of HCl on alkene lead to the formation of alkyl halide, and the addition of, so it is governed by Markovnikov rule or Markovnikov rule, which says, in short, you can say rich gets richer. Okay, what it means, rich gets richer means the H plus will join itself to the carbon bearing more number of hydrogen atoms. So this is the carbon atom having 2 hydrogen, and this is the carbon atom doesn't have any hydrogen. So I'm going to put H plus on this. I'm going to put Cl minus on the carbon atom bearing less number of hydrogen. The negative part is going to attach itself to the carbon atom bearing less number of hydrogens. Okay, this is how it has happened. Okay, and this is the major product. Okay, the major formation of major product is governed by Markovnikov rule. Is it clear? Darshan, Pavitra, Hanifa, is it clear or not?
Yes, sir.
Okay, so this is going to be the minor product. Minor. Why minor? Means it will be formed in less amount. Okay. Why it will form? Because this is not as per Markovnikov rule. Clear? You can see over here. So you have put H on the carbon atom bearing less number of hydrogen, but you should put H to the carbon atom bearing more number of hydrogens, right? So I hope that is clear to all of you.
Yes,
Okay.
sir.
So, but why it happened? What is the reason? Darshan and Hanifa, tell me, what is the reason for Markovnikov rule? What is the controlling factor? Why it happens actually? Yeah, who can tell me? Yeah. Why the addition of HCl, HBr or HI, or if I see general it is HX, occur in a Markovnikov fashion, okay, on double bond? Why? Yeah, who can tell me? Hmm. Yeah, actually, the thing is, it is governed by the stability of the carbocation. I told you just now that the addition of HCl, addition of H plus on double bond is occurring and in two steps. One is the attack of H plus will lead to the formation of a carbocation. Okay, and that carbocation which is formed need to be stable. So you choose the way in which the carbocation formed is the more stable one. Okay, so let me show you the two methods. Suppose the H plus is there, and H plus will get attracted toward the double bond of an alkene, and it can come on right hand side, it can come on left hand side. There are two options. So this is path 1 and this is pathway 2. And suppose if the H plus is coming from this side, what happens? This double bond will come this side and the plus charge will go on that side. And if the H plus is coming from this side, so double bond will be taken by the H plus and the plus charge will come on this side. Okay. So which is the more favorable way? Is it the pathway 1 or the pathway 2? Yeah, Pavitra, Darshan, tell me. Is it the pathway 1 or pathway 2? Which is more favorable, Samaira?
Pathway 2.
Pathway 2. Okay, the pathway 2 is like this. The H plus is coming towards the carbon atom. So the plus charge, this is the pathway 2. Look here, H plus is joined itself to the middle carbon and the pi bond has shifted towards the H plus and that has created a plus charge on, you can see, on the CH2. Is it clear? Does everyone agree that it is the pathway 2? And what happens if the H plus join itself to the double bond by adopting first pathway? Okay, this is the first pathway. Okay, the H plus will come and join to CH2 and the double bond will shift it towards, okay, on the right hand side. Okay, you can see over here, and the plus charge will come on the middle carbon. And because the attack of H plus, you can see, is the RDS, rate determining step. Okay, it is a slow step, it is a difficult step because there is a breaking of bond, because there is a formation of C plus, which is a reactive thing, okay, which is unstable. Okay, that's why it is a difficult step. So if it is a difficult step and if there are two options, okay, either this way, either the pathway 1 or pathway 2. you are going to choose the pathway which lead to the formation of a more stable reactive intermediate. So the intermediate which is forming is the carbocation intermediate, right? Clear? And the carbocation intermediate, you need to choose the carbocation which is more stable. And the tertiary carbocation is more stable, and this is primary carbocation. Is it clear? This is the tertiary carbocation. Pavitra and Darshan, any doubts on this? Tell me. Okay. Yeah. So good. So which carbocation is more stable, and what are the factors which decide the stability of carbocation? Now you can tell me. All of you can tell me. Yeah. Yes, Samaya, Pavitra, Darshan, tell me. Why the tertiary carbocation is more stable? Yeah. Why it is so? And if you choose to form this pathway 2, that is less stable. Yeah, Samaya, Pavitra, tell me quickly. Darshan. Okay, the answer lies in what carbocation is actually. What is the nature of carbocation? So carbocation is an electron deficient species. It is, carbocation is like this. There is an empty p orbital, which due to which it has a plus charge because there are no electrons. It doesn't have 4 bonds, it has only 3 bonds, as you can see over here. Okay, and it is an electron deficient species. Okay, so wherever the carbocation is forming, just remember, more branched the carbon atom is, more stable is going to be this carbocation. Okay, so carbocation is more stable if the carbocation is more branched, it has more alkyl group connected, and it is less stable if it is less branched, if there are less alkyl groups. Okay, so stability of carbocation, stability order of carbocation is, you can write it, and this is useful not only in this chapter but in all the chapters. Okay, in all the examinations. So tertiary carbocation, secondary carbocation, primary carbocation, and CH3 plus. What do you mean by tertiary carbocation? Okay, what do you mean by secondary carbocation? So you need to look at the carbon atom where the plus charge is. Okay, and then you need to decide that the carbon atom bearing the plus charge, is it connected to one carbon? If it is connected to one carbon, that is a primary carbocation. If it is connected to 2 carbon atom, that is a secondary carbocation. If it is connected to 3 carbon atom, that is a tertiary carbocation. Okay, so for example, this is tertiary carbocation, as you can see over here. You can see this carbon atom which has a plus charge, it is connected to three carbon atom, and this is a secondary carbocation. Okay, because the carbon atom which is bearing a plus charge is connected only to two methyl groups. Okay, and this is the primary carbocation. Okay, and methyl carbocation is just the carbocation in which the carbon bearing the positive charge is not connected to any carbon atom. This is the methyl carbocation. Okay, listen. So this is least stable. So why more branched carbocations are more stable? What could be the reason? Can anyone tell me? Yeah, Samira, Darshan, Pavitra. No problem. If you don't know, just tell me. If you know, you can share it with me. What is the reason? Yeah. Which make a branch carbocation more stable. Yes, Amira. Pavitra. Darshan. Actually, there are two factors. Okay. So if the carbon atom bearing the plus charge is connected to three carbon atom, means it is connected to three branch groups. Actually, these are three, you can think them as three alkyl groups. Okay, and alkyl groups are not very electronegative. They are actually, in fact, electron donating groups. Okay, they are not electron. For example, if you take any electronegative atom, that will try to pull the bonded electron towards itself. But in this case, it is there, the carbon atom bearing the plus charge is connected to three alkyl groups, and these three alkyl groups are electron giving groups because they are not electronegative. So what happens is, so the three bonds which are there, the three bond, the electron density gets slightly pushed towards the carbocation. Okay, it gets pushed towards the carbocation. So normally what happens is, if a bond is there, and if there are two electrons, the electron will be, if the two atoms are exactly same, the electrons will be in the middle. They will be shared equally. Okay, but suppose if an alkyl group is there, like CS3 is there and C plus is there, let's say it is a primary carbocation, because this carbocation C plus is connected only to one carbon atom. So this alkyl group is not electronegative. So it will just push the electrons, bonded electrons slightly towards the C plus. And C plus will benefit from this. Why? Because it will have some electron density to keep with it. Okay, it was already electron deficient. And if it was already electron deficient, and if it gets electron density, then it will become stable. Its potential energy is going to decrease. Okay. So primary carbocation is there. One alkyl group pushes its electron density towards the carbocation, and this is known as plus I effect, inductive effect. You might have studied in your class 11th. Okay, in the organic chapter GOC. Okay, but if you have not studied, not a problem. Don't worry at all, because we are going to discuss each and everything in all the concept of your class 11th. We are going to revise. Okay, so don't worry at all. Just you need to share it with me. Okay. So now if you have secondary carbocation, that is much more beneficial for the stability of C plus, because there are two methyl groups which are giving electron to the carbocation. And if there are, this is a tertiary carbocation, 3 degree, then again it is much more beneficial. Okay, it is more stable than the secondary carbocation, because there are three alkyl groups pushing their electron towards the carbocation, and carbocation electron deficiency will get fulfilled up to some extent, not completely, and it will become stable. Okay, this is one of the reasons. Okay, why the tertiary carbocation is stable. Then secondary, which in turn is more stable than primary, and the methyl carbocation is least stable. Is it clear to all of you? Any doubt in this?
No, sir.
And there is one more reason. Another reason is which lead to the stability of carbocation, and that is hyperconjugation. Okay, so all these things will be useful for you guys. Okay, in your complete organic chemistry. So what is hyperconjugation? Tell me quickly. Who is going to explain me? Yeah. Samira, Darshan, Pavitra. Actually, it is very simple. Suppose someday in your school, if you forget to take your lunch box with you, Okay, you don't have your lunch, you forgot your lunch box at home. Okay, so what happens? Okay, suppose this carbon is there, it doesn't have any electron. Complete 8 electrons are not there, that's why it is plus charge. Okay, so one way in which the methyl group, which is a small alkyl group, can help this carbocation is by pushing its bonded electron density slightly towards the C plus. Okay, this is one way which we discussed, and that makes tertiary carbocation more stable than secondary, which is more stable than primary. Okay, now there is one more way in which this methyl group can help this carbocation to fulfill its electron density. And what is that way? Okay, actually you can see the 3 hydrogens. Okay, and these hydrogens are known as alpha hydrogens. These hydrogens are known as alpha hydrogens. Okay, so it is a hydrogen not of the carbocation itself, but the hydrogen of the carbon atom adjacent to carbocation. Okay, so I have given you example, common life example. Suppose if I go to school, or if you go to school and if you forget to take your lunch box, and you may have friends and they share their lunch box with you. Okay, so term by term. Okay, turn by turn they share the lunch box with you. Okay, so you have not taken your lunch box, you are hungry. Okay, your friends shared the lunch box turn by turn with you, and that, so you can have their lunch box, you can share the food. Okay, and that's how your deficiency is completed. Okay, so same way hyperconjugation takes place. So in hyperconjugation, the electrons of sigma CH bond get delocalized with adjacent cation or alkene or p orbital. Okay, so what in order to show this, okay, what I will do, I will take these CH electrons towards the plus charge. Okay, so these electrons which were there between carbon and hydrogen are taken away by the plus charge. So this is, but it is not permanent. Suppose if you have not taken your lunch box, it will not happen that your friend will share its own his or her own lunch box with you, and you take that lunch box and never return it. That doesn't happen. Okay, you just take the lunch box, you take 1 bite, 2 bite, okay, and you give him back. Okay, right? And that your friend is also having the food from the lunch box, and you are also having, because it is continuously, it is shared mutually among you guys. Okay, so similarly these CS electrons, okay, they get shifted towards the carbocation. Okay, but it is not permanent, they can go back to the original CH. And in the same way, not only this CH bond, there are 2 more CH bonds. Okay, this is known as alpha carbon, or it has 3 alpha hydrogens. So the electron density of this sigma CH alpha hydrogen can go towards the carbocation. It can get delocalized. It can get mixed up with the carbocation, who is in desperate need for the electron density because it doesn't have its own electrons. So I will show one more structure in which I will do the hyperconjugation of this CH. And I will write one more structure in which I will show the third CH bond participating in hyperconjugation with the CH. Okay, this is the way it happens, and this is known as that. So a lot of questions come every time in all the examinations. Okay, this is a very basic thing, and will be useful not only in this chapter but in your complete organic chemistry which you are going to study ahead in class 12, right? So carbocations are stabilized by hyperconjugation, which is a phenomena in which the electron density of the CH adjacent CH bond get delocalized or get mixed up with the MTP or vital of the carbocation, and that makes the carbocation stable. Okay, because carbocation potential energy decreases, and that's how it gets its electrons. Okay, so so I told you that the carbocation, tertiary carbocation, is very stable as compared to secondary, which is more stable than primary. Primary is more stable than methyl. One reason which we discussed was that electron pushing effect, slight, okay, of CC bond. The other effect, which is more prominent effect, is the hyperconjugation, in which the electron density of the CH bond goes and join itself to the C plus. That is called hyperconjugation. Okay, so the carbocation. Okay, so you can see sigma bond that can engage in hyperconjugation, and how many CH bonds are there in the tertiary carbon? In the tertiary carbon, you have 9 CH bonds. Okay, you have 9 alpha hydrogens. Is it clear? 9 alpha hydrogens. And they can contribute their electron density turn by turn to C plus. And that's how your C plus will become stable. Secondary carbocation has 3 and 3, 6 alpha hydrogens. And those 6 alpha hydrogen I have shown you for primary, I have shown you for this carbocation, in which the 3 CH bonds turn by turn participated in hyperconjugation. Secondary carbocation, which is shown here, is having 6 alpha hydrogens. And this is having 3 alpha hydrogens. So more the number of alpha hydrogens, more the deficiency of the carbocation is fulfilled. Okay, is it clear? And the same thing is happening here also. But in methyl, there is no alpha hydrogen at all. You don't consider the hydrogen of the carbocation itself, but you consider the hydrogen of the carbon which is adjacent to the C plus. Okay, that makes it stable. Okay, clear? They're very, very important. So now the next thing is, so carbocation, it is governed by the stability of carbocation. And carbocation, tertiary carbocation, is more stable than secondary, then primary, and then methyl. And it is because of the inductive effect and hyperconjugation. And Pavitra and Samaira, how you are going to measure the inductive effect? Inductive effect, you just look that how many alkyl groups are there, that's it. Which is not a very strong effect. But hyperconjugation, what you do? So wherever the carbocation is, you count the CH bond adjacent to the carbocation. Okay, and that will make you understand that why tertiary carbocation having more number of alpha hydrogen is more stable. It's just like suppose if you have more friends, and if it forgot to take a lunch box, so more friends will share their tiffin lunch box with you. Okay, and you will not feel that you have not brought your own lunch box. Okay, that's how it happens. Okay, so now this question. So what is the major product? What is the IUPAC name of the product which is found, major product found when HI is added to 2-methyl butene? That you need to know. Yeah, what is the IUPAC name? Samara and Pavitra, tell me. IUPAC name of the product, major product, which is formed when HI is added to 2-methyl butene. Yeah. Tell me quickly. Yeah, who is going to explain me? Samara, Pavitra, tell me. Yeah. So you need to think how you are going to attach HI. H is going to attach itself to the carbon atom bearing more number of hydrogen. The rich gets richer. Okay, that's the quick trick to remember to do Markovnikov addition. So H plus will come here. Okay, if H plus will come here, the pi bond will shift like this. Okay, and the plus charge will come here. That is good because it is tertiary carbocation. Okay, and here you are going to put the I minus. So that is going to be the major product. And what is the IUPAC name of this product? CS3I. Okay. So IUPAC name, you need to consider the main chain first. Okay, longest continuous carbon chain, which is known as parent chain. So it has 4 carbon atoms. Okay, in the parent chain, and on second carbon you have methyl and iodide connected. Okay, so it is 2 iodo 2 methyl. Okay, these are the locants which tell us iodo means iodine. I am going to write first because I comes before M in alphabetical sequence. 2 iodo 2 methyl, and then the name of the parent chain butane. Okay, that is a major product, and this is the product which is formed by considering the stability of carbocation. Okay, and then you attach the I minus on the more stable carbocation. So it is the Markovnikov product, or it is the product which is formed by Markovnikov rule. On the other hand, this is the anti-Markovnikov product. Okay, when this will form, this is going to form when you have created a plus charge on secondary carbon, and this is going to be less stable as compared to the tertiary. Okay, because it is outside and it is having less branch. Okay, less number of alpha hydrogen, less hyperconjugation. Okay, and so this is the anti-Markovnikov product. Okay, so this is going to be the minor product. Is it clear?
Yes, sir.
And similarly, you need to know what is it. So these are the questions which come very frequently. Okay, so what is the IUPAC name of this? In all the examination, NEET, JEE, these are the most common questions which are asked. Most common question which are asked in NEET and JEE. So what is the IUPAC name of product? Major product which is formed by addition of HBr on 1-methyl cyclohexane. Yeah, tell me quickly. Pavitra, are you getting any doubt? Samira, what is going to be the major product?
Will be 1 bromo, 1 methyl, cyclohexane.
Yeah, 1 bromo, 1 methyl. Yeah, H plus. There is already one H. Okay, how you are going to make out? So count the number of lines, number of bonds. So this carbon has 3 lines coming out of it. One is double. So carbon always make 4 bonds. And if you see 3 bonds, the 4th one is not mentioned, not written. It is hydrogen. Okay. So you are going to attach the H plus coming out of HBr on this carbon atom. Pi bond will shift outside. The plus charge will come on this. It is a tertiary carbon. Okay. And this tertiary carbon, you are going to attach Br minus. So that is going to be the major product. 1 bromo, 1 methyl cyclohexane. Okay. And this is the anti-Markovnikov product. Okay. This is the Markovnikov. The product which is formed by considering the stability of carbocation is Markovnikov product. Is it clear?
Yes, sir.
Samira and Pavitra, is it clear or not?
Clear.
Okay. So now tell me what is the major product of this reaction? Yeah, this is little bit. You need to think. Yeah, who is going to tell? Just write IUPAC name. Tell me quickly. Yeah, these questions, lot of questions we have, okay, in our JEE, NEET, very common questions. So what is the IUPAC name of the product which is formed by addition of HBr on 3-methyl butanene? Okay. So where you are going to put H plus? First, you need to think that. So you need to put H plus on the double bond, right, Samira? But will you connect it to carbon number 1 or carbon number 2?
1.
1. Why 1? Why not 2? Yeah, Pavitra. So Markovnikov rules, shortcut you can apply. You are going to attach H plus to the carbon atom bearing more number of hydrogen. Or you can think of the carbocation which can form. If you connect H plus to the second carbon atom, the carbocation will form on the first carbon, which will be primary. But if you attach H plus on the 1-degree carbon atom, the carbocation will form on 2. Okay, so that is more stable. And what is the product? Yeah, tell me. Samira, Pavitra. Yeah, tell me quickly.
2-bromo 3-methyl butane.
Yeah. So I'm going to put Br minus here because whatever the carbocation which I formed, I created that carbocation. And then I will put this Br minus. Okay. So 2-bromo 3-methyl. I'm going to do the counting from this side because B comes before M. Okay, 2-bromo 3-methyl butane. But whatever you thought is correct, but this is not the answer. What could be the reason? Yes, Samira, Pavitra, tell me quickly. You have not told me anything wrong. Whatever you said is correct, but then why the answer is incorrect? It is because you missed one thing. There is one very important property of a carbocation that we need to discuss. Till now we have not discussed. I need to know that whether you know it or not. Yeah, this is not the answer. Okay. Yeah, Pavitra, you can try it. The answer is this one. This is not the answer. Samira, what has happened to it? Yeah, tell me. How come the Br can come to the tertiary carbon effect? The carbocation is there on the second carbon. How come the Br can go and join itself to this? Yeah, Pavitra, Samira, tell me. You need to put Br only to this carbon, but that is not the answer. The answer is actually something else where we have not expected Br. The Br has attached itself to the tertiary carbon, and the tertiary carbon was not having any carbocation. Yeah. So actually, you need to know a very, very important property of carbocation. And what that important property is, what it is. Samira, Pavitra, tell me quickly what it means. Yeah, quickly tell me. Yes, it is rearrangement of carbocations. Okay. So what this rearrangement is? So carbocation actually, whatever the carbocation. So first we need to discuss that what carbocations can form 1 degree or 2 degree. Okay. Out of those carbocation, we already made a stable carbocation. Out of the possible carbocation, we made a stable carbocation. But my dear students, suppose if the carbocation can become more stable by moving on to adjacent carbon atom, then it will get shifted to adjacent carbon atom, but the shift is going to happen only if it is becoming more stable. Then only we are going to do that. Otherwise, we are going to leave the carbocation as untouched. Okay, just we will put the Br minus or I minus on that cation. But if the carbocation can become more stable by moving on to the adjacent carbon, then we should definitely move that carbocation to the adjacent carbon. And this phenomena is known as shifting of carbocation or rearrangement of carbocation. So always, 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 you need to check the rearrangement of carbocations. Okay, whether the carbocation can become more stable by moving on to the adjacent carbon. If yes, you need to shift that carbocation to that adjacent carbon, and then final group like Br minus or I minus will need to be attached only to the cation which is formed after shifting, more stable cation after shifting. Okay, the shifting is known as rearrangement of carbocations. Okay, how it happens? Look here very closely. So H plus is there. So first you need to make a more stable carbocation. So I will make carbocation on this carbon. Secondary carbocation I have generated by attaching Pavitra and Samira H plus, right? So you created a secondary carbocation. Now check the surrounding carbon atom, wherever the carbocation is. It is not only in this reaction, but in every reaction in which a carbocation is forming. Be careful. It can be used in all the reactions. Okay, clear?
Yes, sir.
Yeah. So now this is primary, and this is a tertiary carbon because it is connected to 3 carbon. So now we know, we just now discussed that the tertiary carbocation is very stable because it is more branched. It has the carbocation surrounding the carbon have more alpha hydrogen, and they can contribute more towards the hyperconjugation. So we need to bring somehow, we need to bring this carbocation from secondary to tertiary carbon. Now, how to bring that carbocation on tertiary carbon? That's the problem, because this tertiary carbon is not a carbocation and its bonds are already completed. It is connected to 4 different groups, 4 groups, methyl, hydrogen. It is already connected. So how will you bring carbocation to this carbon? Okay, so That is by shifting of a group, one of the group which is connected, because this carbon is complete. It is not a carbocation, but carbocation wants to become more stable. So carbocation will come on this carbon. So if the carbocation come on this carbon, one group should go on that carbon along with the electrons, so that the carbocation can come on this carbon. Okay. So who will go? Okay, who will go? Who will get shifted? So this is known as shifting of alkyl groups. Okay. So first check who all groups are present, what all groups are present on this tertiary carbon, and then decide which group can shift more easily. So, and that is decided by migratory aptitude. So migratory aptitude says the H along with the electron pair can get shifted most easily. So hydride, then phenyl group can get shifted after hydride, and then you have alkyl groups which can get shifted, and within the alkyl group, tertiary carbon, secondary carbon, primary carbon, then methyl. These groups shift if you have different groups, and if you need to bring carbocation on this side, and you need to decide which group need to be shifted on the carbocation side to bring carbocation on this side and make it more stable. So my dear student, the answer is you need, if there are different groups possibilities, you need to decide on the basis of migratory aptitude. The migratory aptitude says the has more migratory aptitude than phenyl, which is having more migratory aptitude, then tertiary, alkyl group, then secondary, then primary, and methyl. So on this carbon, you need to think what all groups are present. You need to compare their migratory aptitude. And you can see there are two methyl and there is one hydrogen present on this carbon. And as per the migratory aptitude, H minus will get shifted to that carbocation because it is having more migratory aptitude. Okay, clear. So this will get shifted on that side. What you will get? This one. This is known as hydride shift. The CH3 can also shift, but not in this case because the out of hydride and CH3, the hydride is having more migratory aptitude. Okay, you need to remember this migratory aptitude also. So H will shift along with the electron pair to this carbon. So because H has shifted along with the electron pair on that carbon now will have complete 4 bonds and it will not have positive charge now. But where the positive charge will come? It will come on the group from which the alkyl group has been transferred. Okay, so the new carbocation will appear on this, and this is known as rearrangement of carbocation or shifting of carbocation. The shifting will always happen if you have a more stable carbocation, if the resulting carbocation is more stable than the previous carbocation. And while doing the shifting, you need to consider which group to get shift on that carbocation to bring carbocation on this side with a more to make carbocation more stable. You need to compare the migratory aptitude. Okay, you need to remember the migratory aptitude, and you need to do the shifting of the alkyl group which is having highest migratory aptitude. Okay, so this is the way new carbocation, and now this is tertiary. Okay, now it can't go anywhere else. Okay, this is already tertiary, this is already more stable. You can see here 1,2 hydride shift has happened. Okay, because the carbocation want to come on this carbon which is tertiary. Okay, after hydride shift, the hydrogen has moved, that yellow part has gone to that carbon, the carbocation has come here, and now because it has already become the most stable tertiary, now it can't shift anywhere else because on the either side you have primary carbocation, primary carbon, or secondary carbon, and shifting carbocation on those carbon will not be a good thing to do because those are less stable. So you will keep the carbocation here only. Now no shifting, it is already completed. Tertiary carbocation, put the Br minus, okay, make the final product, and that is the major thing. Okay, so Markovnikov rule, addition of HCl, HBr, HI will take place via electrophilic addition reaction, in which the H plus is going to attach on an alkene first. It will lead to the formation of a carbocation. Okay, the addition is governed by Markovnikov rule. As per this rule, more stable carbocation is formed as an intermediate. Okay, out of the two cations on alkene, more stable carbocation need to be formed on alkene. Okay, then once a more stable carbocation is formed, you need to check whether the carbocation gets shifted one more step ahead to the next carbon if it is becoming more stable further. If it is becoming more stable by shifting on to the next carbon, you will do that. This process is known as rearrangement of carbocation. Okay, rearrangement must be done as per migratory aptitude by considering the migratory aptitude of the groups. Okay, the new carbocation is formed which is more stable than the previous one by shifting of a group. Okay, this whole process is rearrangement, and once the rearranged carbocation, the more stable carbocation is formed, then you put that final I minus or Br minus, and then you get the final product. Okay, so all these things you need to consider while doing the addition of HX on alkenes. Is it clear to all of you? Samaira, Pavitra, very important. Not only in this chapter, it will be useful in all the chapters in alcohols, in aldehydes, ketones, in all the next upcoming chapters. It will be useful. So I hope it is clear to all of you. Any doubt in this?
No, sir.
Okay. Yeah. So what you need to keep this in mind. It's very important. Most of the students forget migratory aptitude, why it need to be done. Okay, what is the thing? Then the next thing is, so normally if you add HBr, normally if you add HCl, normally if you add HI, HF you don't normally add because HF the ionization occur very less. It is not a very strong acid. You can do that also, but not very much favorable. Okay. So you mostly add HF, HCl, HCl, HBr, and HI. The addition occurs by Markovnikov rule, which is governed by the stability of carbocation. That's what we discussed. But is there a way to add HX in reverse manner on double bond? The answer is yes. But it is only for HBr. Only for HBr. Okay. So among all HX, and this is the reverse way of adding HX, but not all the HX can add in reverse way. Only one type of HX, that is HBr. So it is known as anti-Markovnikov addition of HBr. It is also known by the name of, can you tell me what is the other name for this type of addition? Okay.
Peroxide effect and Kharash.
Yeah, peroxide effect and Kharash effect. Yeah. Why it is known as peroxide effect? It is known as peroxide effect because it HBr normally it will attach itself in a Markovnikov fashion. Okay. The rich gets richer, the carbon atom which has more hydrogen, the hydrogen will connect to that carbon only. and the carbocation will form on the secondary carbon in the middle, and there you have Br connected. So this is Markovnikov addition. This anti-Markovnikov or reverse addition of HBr will be exhibited in the presence of peroxide. Okay, clear? So which peroxide do you choose? So that's why it is known as peroxide effect. And only HBr shows peroxide effect. That also we will discuss why only HBr shows. Right, Pavitra? Is it clear?
Yes, sir.
Good. So only HBr shows peroxide effect. It means it is adding in a reverse manner. And that too only in the presence of peroxide. So what all peroxide do you use? Which peroxide is the most famous which you use for this reaction? Yeah. Samaya, Pavitra, can you tell me? Actually, it is benzoyl peroxide, which is the most commonly used. Okay. Or you can write it like this also. This is the peroxide linkage. OO linkage is there. Sometimes it is written in short, normal, general way, in a very general way as ROOR. This is the peroxide. So peroxide, presence of peroxide changes the way of addition of HBr. HBr only among all HF, HCl, HBr, only HBr exhibits peroxide effect. Means in the presence of peroxide, it will be added in a reverse manner. What all peroxide do you use? The most famous one is the benzoyl peroxide, though other peroxide can also be used. You need to know that they must have OO bond. Okay. So these are the three questions which we can try. So let's start with this question, which is the normal addition of HBr. It is Markovnikov addition. Okay. H plus is going to attach on this side. The carbocation is going to form on the upper carbon, which is a tertiary carbon. And there is no rearrangement which can be done because it is already tertiary, it is already more stable. The Br minus will go into this carbon. Okay. Is it clear?
Yes, sir. Yes, sir.
So this is a major product. This is Markovnikov addition of HBr. But if you take peroxide also along with HBr, the mechanism changes. There is a change in mechanism which happens because of the presence of peroxide, and this is electrophilic addition reaction earlier. So peroxide changes the way in which the HBr breaks. In the presence of peroxide, it breaks as radicals. Radicals are species having that one unpaired single electron. So HBr, this is not electrophilic addition reaction. This is free radical addition reaction. Okay. Now this is free radical addition reaction, and because the peroxide is there and it is going to happen just by we have not discussed the mechanism and everything in detail. Just by the outer knowledge and the name and all, we can tell that the product which is formed is just the reverse of the norm Markovnikov addition. Okay, this is anti-Markovnikov addition. So here you are going to put H, and on this side you are going to put Br. Okay, so just the reverse of this product. This is peroxide effect. And what happens if we take HCl and peroxide effect? It doesn't matter with HF, HCl or HI. Only HBr shows peroxide effect with HF, HCl or HI, whether you take peroxide or you don't take peroxide, it's not the matter of concern. Do remember this, because this is the question which is asked in all the examination, very basic question. So because we have peroxide or anti-Markovnikov of addition so much into our mind that when we see HCl and peroxide, we do the anti-Markovnikov of addition of HCl also in or peroxide effect. We apply the peroxide effect on HCl, but we need to remember only HBr shows peroxide effect. HCl is going to join in a way in which it was joining without peroxide, so it is going to be the Markovnikov addition only. Peroxide presence or absence of peroxide, you can write it in your notes, will not affect the way of addition of HF, HCl and HI. Only HBr addition get reversed in the presence of peroxide. That you can write. Very, very important. Okay, so this is Markovnikov addition. You can write two spelling, Markovnikov or Markovnikov, okay, because it is a Russian name, you have both the spellings, okay, right? You will find both the spellings in the book, so don't get confused, right? So this is still Markovnikov addition. Even in the presence of peroxide, you should not feel surprised, and this is a mistake which all of us do, okay, in examination, because of the examination pressure. It has been asked in almost every examination, JEE, NEET, everywhere, even in advanced, okay. The advanced also it has been asked. NEET as it has been asked, okay, right? So let me ask you one question from NEET itself, but it is not only related to NEET, it is related to JEE also, okay. Let me write it. Very basic question. Though this question is from NEET 2021, but it is the appropriate candidate for JEE also. Such question, but different structure is given in JEE question. Okay. So what is the major product of this reaction? Very simple question. I hope both of you can do it very quickly. I'm going to write the options for you. Yeah. What's going to be the final answer? Yeah, Samira, Pavitra.
First one, sir.
Yeah, it is anti-Markovnikov addition. That's it. So normally H attaches to the carbon atom bearing more hydrogen if it is Markovnikov, but the presence of peroxide will make it anti-Markovnikov. So H is going to attach itself to the carbon atom bearing less number of hydrogen. Okay. So now, and the Br on the outer carbon. So the first one is the right answer. Very good. So now this is incorrect. Okay. And if someone doesn't know, if someone do HBr addition in a normal way, Markovnikov addition, then he or she may get this answer. And if someone do Markovnikov addition of simple HBr and also do the rearrangement, which will always happen on its own, okay, you will get this answer. But as of now, because peroxide is taken, only the first one, anti-Markovnikov addition, is the answer. It is not a carbocation mechanism, it is a free radical addition mechanism. Is it clear? It's a free radical addition mechanism. Normal HBr addition is a carbocation or electrophilic addition reaction. So why it is a free radical addition? Normally, in the absence of peroxide, HBr being polar and acid will break in this manner, and this is known as heterolytic cleavage. Heterolytic cleavage means the bonded electron were taken away by one atom, and that will have minus charge on itself. The other atom will have positive charge. So this is Markovnikov addition of HBr. But if you take peroxide actually, how peroxide changes the course of reaction? Peroxide has OO bond. Okay, that OO bond actually breaks into radical very easily. Okay, it is weak, it breaks very easily by giving some energy. Okay, so peroxide we are taken. And that actually changed the course of reaction. If you heat it, Pavitra, Samara, it will break into radical. You can see this single electron. There will be no charge because the bonded electrons are distributed evenly between the two atoms. So this is known as homolytic cleavage. And if you have this O radical, because of the peroxide, it will break HBr in a new way. Okay. Earlier HBr was breaking it as H plus and Br minus. Now in the presence of peroxide, you have RO radicals being generated by the peroxide, and these RO radicals will go and take H radical. Why H radical? Why not H plus? Because it's already having one electron. So it will take H with one electron, and so it will become alcohol ROH, which is a stable. Okay, and what is left behind? You are left with the bromine radical. Okay, this bromine radical, what it will do? This bromine radical is again a reactive intermediate. It will go and join itself to alkene. Okay, alkene has a double bond. The double bond has two electrons, pi electron, two pi electrons. The bromine already has one electron with it, so it will join to the double bond. Double bond has two pi electrons, say 2 sigma, 2 pi. Only the pi electron, pi bond will break because it is weak. So Br will join with one of its electron to the carbon atom of the pi bond, and it will join in a way such that a more stable radical is formed. Okay. So again, the same thing we are going to apply here. Only there H plus was adding to double bond, and we discussed that the H plus will attach itself in a way such that a more stable carbocation was formed, which was formed on inside of the alkene. Here the Br radical is joining because peroxide actually changed the course of reaction, and that has led the HBr to form Br radicals. Br radical will attack on double bond, and they're going to join itself to the double bond such that a more stable secondary radical is formed. Okay. It is not going to come inside. Okay, if the Br radical come in inside, the radical will form outside. That is not going to be stable. So this radical is going to form, and this radical again, it is not going to stay as it is because it is intermediate. It is going to attack on another HBr molecule, fresh HBr molecule, which has not been cleaved by peroxide, and it will take H radical and will generate another Br radical. This Br radical will go and search another alkene, and that's how the reaction will keep on progressing. Okay, so peroxide will break into radical. It will attack HBr and it takes away H. Br radical will form. Br radical will attack on double bond. More stable carbon radical will form, and then H radical will join to that carbon radical. So this is how the course of the reaction is seen, and this is how the product which you get is not the normal product which you obtain when you add HBr to alkene, but it is just a reverse product. And it happens only on unsymmetrical alkenes. Symmetrical alkenes, there is no point of taking peroxide because they are always going to give only one product. Okay, so wherever you have unsymmetrical alkene, HBr can be added to that unsymmetrical alkene in a Markovnikov way by taking simply HBr, or in an anti-Markovnikov way by taking HBr along with peroxides. Okay, so I hope it is clear till this point. It's very, very important, and the concept which we discussed will be useful for the upcoming chapters. Okay, so let me end today's class. Already we are running out of time, so just try some more questions. Let me know if there is any doubt in the next class. So let me say good night. Bye bye everyone. Take care.
Thank you so much, sir.
Okay.